Hello and welcome to Sevenoaks Campaigners Online. We're hoping that this is going to be the first one of one or two videos on making music from scratch. This does come with an apology to parents for any cacophony that this may produce around your household. During this particular video, there is going to be a range of difficulty over the things that we do. Some of the little experiments we do will be easy ones, which most people should be able to follow without too much difficulty. Some will be a little more challenging. We also will need to do some science calculations during the course of this. Now, if you're at a primary school, you may find that those calculations look a bit complicated, and you might just want to pass over those to see the results and to use the results. If you go to a secondary school, might I suggest that you do try to follow through the calculations, because it is the sort of thing that you will need to know about. We're going to begin by making a musical note from two drinks bottles. These drinks bottles are pretty similar to each other. They're half-litre bottles, and you should be able to make a note by blowing across the top of the bottle. Now, you do have to blow in just the right way, so it takes a little bit of practice to try and get this to happen. But I'm going to try to do it with the two bottles, and I want you to hear the two notes. They're both the same sort of bottle. Let's see what we get. And the other bottle. Both the same note. You'll notice there I had a bit of difficulty getting the notes, and I have practiced doing this. So if you don't get notes at first, do persist with it. The notes from the two bottles were the same, but we can change the notes by putting water into the bottle. So let's put water in one of the bottles and see what happens. So we'll just pour a little bit of water into the bottom of one of the bottles. And then let's try blowing the two bottles to see whether that made any difference. So I've got one bottle, this is the bottle with the water in, this is the other bottle. Let's blow the original bottle with no water. And the one with some water in. And you can hear the note has changed. The pitch has gone higher as we've added water into the bottom of the bottle. So I could gather a whole lot of bottles together, and I could make a whole lot of notes to make a musical instrument. It will be extremely inconvenient, because having to move from one bottle to another to change the notes would be very difficult to make any sort of tune. But nevertheless, it will be possible to do this, so you might want to give that a try. Something that might turn out to be a whole lot more convenient is if we could make sound just by blowing across pieces of tube. So I've got here some plastic tube. It's just ordinary bits of plastic tube. Let's try blowing across one of those to try and make a note. So I've got a little piece of tube here. That doesn't really work very well. It's difficult to get anything out of it. And what I did get eventually was not a very useful note. The key to this is not just to try and blow the tube, but to block the end. So if I put my thumb over the end of the tube and then blow it, I can get quite a nice note, and comparatively easily. But not all tubes blow as easily as each other. Let's have a look. If you want to make a note with a high pitch, then you need the tube to be fairly short. And if it's short, you don't want it to be too wide. It becomes harder to get the sound out of it. If you want to make a low note, then you need a longer tube. And longer tubes might need to be a bit wider, though wider tubes do gradually become harder to get a sound out of as well. The distance across the tube would be the diameter. And if you want a tube to make a sound easily, it seems to work if the length of the tube is between 7 and 14 times the diameter. So if you had a tube that was 10 times as long as it was across, if its length was 10 times its diameter, then that seems to work quite well. So let's try some different tubes. Here's my first short tube, and this is one that blows quite easily. If I take a tube that's similar sort of length, it's a little bit longer, but it's wider, it's harder to get a note out of that. Remember, you do need the end blocked, and when I say you need the end blocked, it has to be absolutely blocked. The slightest leak at the end and this doesn't work. So with the end blocked, it's a wider tube. I can get a note out of that, but it's not as easy as the narrower tube was. And you need to bear in mind that I have practiced doing this. As the tube gets longer, the pitch of the note goes lower, so here is a longer tube. And for a longer tube still, this is a wider tube, so it is a bit more difficult to blow, but you should hear a low note if I get the bottom sealed. And so for that sort of length of tube, you would need it to be wider if you want to be able to get the note. But this sort of tube is a bit harder to blow than the narrower one that I started with. So you could have a whole set of tubes with different lengths to make different notes. You glue them all onto a frame and you would get what we often refer to as a pan flute or pan pipes. And it wouldn't be too difficult then to move from one tube to another to change the notes. This is a set of professionally made pan pipes or pan flutes, but we could attempt to do something like this for ourselves. You will see now there is going to be one problem. It's easy enough to move your mouse from one tube to another, but it wouldn't be quite so easy to move your thumb, because you do need the bottom end of the tube blocked. So we will need to have a system of sealing the ends of the tubes. So we'll show you how to do that. Bear in mind that if you're going to seal the end of the tubes, you do need to make sure that you've cut them straight so that the ends of the tube aren't wonky. Otherwise it's going to be very difficult to seal them. If you've watched some of our other videos, you won't be in the least bit surprised to discover that a cereal packet comes into this. Now the cereal packet has got a shiny side to the cardboard and a dull side. We're going to use the shiny side to go inside the tube because we're hoping the shiny side would be a little bit waterproof. When you're blowing a tube, it's going to get wet inside from the moisture in your breath. But despite this being shiny and a bit waterproof, we're going to try and waterproof it a little bit more by using PVA glue. And what we're going to do is put a thin layer of PVA on the shiny side of the cereal packet. So I'm just using a bit of kitchen roll and some PVA to coat the shiny side. That will take a while to set, so we'll need to come back to that once it's dry, so perhaps in 3/4 of an hour. And the other things you're going to need for making the seal at the bottom of the tube, you will need another sort of glue, a hobby glue or a glue gun, or something like that, so that we can glue the little bit of card we're going to make onto the bottom of the tube. The PVA is not really very good for that. And you will need some pencil and scissors. So we'll come back to this once the glue is set. So here we are. Our PVA has set. This doesn't look any different now because the glue sets clear. We've got our glue gun ready, and this is our piece of pipe that we're going to seal the end. By the way, we will explain exactly what pipe we're using to make these instruments with, because it turns out to be quite a good pipe to use, so we'll explain what it is and how to get it. We're going to work from the back now of the cereal packet, and we need to cut a little circle. So we just put the pipe on the cereal packet and draw around the bottom, and we do this for as many pipes as we want to seal. And then once we've done that, we cut out that little circle as neatly as we can. Now I've already done one of these, and so here's the little circle I've ended up with, and that should fit over the end of the pipe. Remember, the end of the pipe needs to have been made smooth and it needs to be cut square. By the way, to sand the end of the pipe to get it smooth, I tend to wrap my sandpaper in a block of wood so that I get a fairly flat surface to sand with. So once we've got that, we're going to just put a layer of glue from the glue gun round the end of the pipe. And once we've got that, we push the circle onto it. Shiny side goes in the pipe. We press that on. Now that does need to be a perfect seal. If there is the slightest gap in that, then you'll find that the tube won't really sound. So we'll do it and then let's test it. So we blow across the end. Perfect. And we don't need to use our thumb now. If that didn't work and you have learned how to blow these, then you haven't sealed the end correctly and you'll need to just put a bit more glue around to make sure that it is sealed properly. Now you could just take a whole bunch of these of different lengths, almost a random selection, and glue them onto something to make an instrument. But you might want to have your notes match with other instruments. So you might want to have it tuned so that it would play with a piano or something like that. We can work out how to do that. Now, I need to set up an experiment just to start showing you how we do all this. We begin with a trip to the beach. Now, here we can see there's a girl standing in the water and there are waves coming towards her and lapping over her. Well, let's just stop the waves for a moment and have a look at the distance between the crests of the waves. That distance from one crest to the next crest is called the wavelength of the waves, and in this case it's about 2 meters. Now if we get the waves to go again, we could also look at how long it takes from one crest to arrive at the girl for the next crest to get there afterwards. And I just did a rough count on this, and I reckoned that that was about 5 seconds from one crest to the next crest. So we could now ask ourselves, how fast are those waves moving towards the girl? Well, the waves move 2 meters in 5 seconds. So that would be 2/5 of a meter per second. We took the wavelength and we divided by what we might call the time period, the time from one wave hitting her to the next one. And that gives us the speed of the waves is 2/5 of a meter per second. When we were looking at water waves, we saw the waves were going along the surface of the water and we could see the crests of the waves moving. Well, this represents a guitar string, so across there. And if we pluck the guitar string, we should make waves that would go along the string and would bounce back from the end and go backwards again. And in fact the waves would bounce backwards and forwards along the end of the string. So that's what we should see if we pluck the string. But it isn't. What we see when we pluck the string is that the middle of the string is making big vibrations. The ends of the string don't seem to be vibrating at all, and it really doesn't look as though there are any waves going backwards and forwards down the string. But there are. This effect, where the middle of the string is vibrating a lot and the edge is not vibrating at all, is what we call a standing wave. It doesn't look as though the wave is moving. and it's the result of two waves meeting each other. The wave going down the string meeting the wave reflecting back. And when a wave reflects back on itself, you get what we call a standing wave, a wave that doesn't seem to move. It just seems to have these areas where it vibrates a lot and areas where it vibrates a little bit. Now, when I just pluck the string, of course, the vibrations die away. So I'm going to keep them going so that we can have another look with the machine here. So you'll hear as the machine comes on. And now we can see the waves with big vibrations in the middle and nothing at the end. As it turns out, the distance now between one still place and the next still place is half the wavelength of those moving waves. When it comes to a vibrating guitar string, it also turns out that there is not just one wave going backwards and forwards down the string. There are lots of waves. We don't really get to see them. When we pluck the string, it really looks as though there's just one vibration going on. In fact, there are a lot of different vibrations going on, and I can show you some of those by using the machine. So here is that main vibration. We call that one the fundamental vibration. But if we get rid of that one, you'll find that there are other ways that this string can vibrate. And you can hear the frequency of the sound going up with it there. There is another way that the string can vibrate, where the middle of the string is still, the two ends are still, and there's big vibrations here and here. And on a guitar string that would be happening at the same time as the fundamental. Again, the distance from one still place to the next still place is half the wavelength of the wave that is going backwards and forwards down the tube, or down the string I should say. So this frequency is actually at twice the frequency of that fundamental wave. It's at half the wavelength and twice the frequency. And again, this is not the only one that's going on in addition to the fundamental. If we keep going up the frequencies, the string can vibrate in yet other ways. And here, there is a place where the string has got two still places. The vibrations now aren't as big, but I'm hoping that you can still see them. If I try and get it just right, which I'm failing at the moment. We could carry on up the frequencies and you would find there were many higher and higher frequencies, and the guitar string is actually vibrating with all of them to some extent. The important things to remember: a standing wave is caused when a wave reflects back on itself. And so there is a wave going backwards and forwards along the string, but it looks as though nothing is moving, and that's the standing wave. And on a standing wave, the distance from one still place to the next still place is half the wavelength of the wave that is going along the string. If I just run this back down the frequencies, you'll see those other ones that we found on the way. There should be twice the fundamental frequency, half the fundamental wavelength, and back down to the fundamental, where the biggest vibrations are in the middle and the end is just still. When we're blowing across a tube, something similar happens to what we saw on the string. This time it's sound waves going through the air down the tube rather than the waves on the string. But the sound waves go down the tube, they bounce off the bottom and come back up again, and we get a standing wave set up inside the tube with a still point at the bottom of the tube and big vibrations at the top. Now that would tell us that the length of the tube should be a quarter of a wavelength. Unfortunately for us, that doesn't quite work. There are all sorts of peculiar things happening to the sound waves at the top of the tube, at the open end, And the result is that the quarter of a wavelength isn't the physical length of the tube. It's actually the physical length of the tube plus a bit more. We call the bit more an end correction, and it seems by experiment that the end correction, if you're blowing the tube in the way that we are, is about 8 millimetres for every 10 millimetres diameter of the tube. So a quarter of a wavelength is equal to the length of the tube plus about 80% of the diameter. So here comes the arithmetic to work out how long we need to make our tubes. When we were dealing with water waves, we worked out the speed of the water waves by saying that it was the wavelength of the waves divided by the time period. For many of the waves that we deal with, the time period would actually be very, very short. The waves have a high frequency. So rather than take wavelength and divide by the time period, we take wavelength and multiply by the frequency. That turns out to be exactly the same thing. And so we have the speed of sound is the wavelength of the waves multiplied by their frequency. Frequency is the number of vibrations per second. If we want to work out the wavelength of one of our sound waves, we can rearrange that formula and we get that the wavelength of the waves will be the speed of the sound divided by its frequency. Now, the speed of sound in air is about 343 meters per second at our normal room temperatures. You'll gather from the fact that I had to mention temperature that the speed of sound doesn't stay constant, but it's around 343 for the normal temperatures that we live at the surface of the Earth. So, if we want to work out the wavelength for a frequency of 880 vibrations per second, we can use that formula. By the way, we don't keep saying vibrations per second. We call that 880 Hertz. Hertz is not a car rental company in this case. This is named after somebody called Heinrich Hertz from the 1800s who did a lot of work on waves, so this is named in his honour. So, where were we? If we want to work out the wavelength of sound when the frequency is 880 Hertz, we take the speed of sound, 343, and divide by 880. And that gives us a wavelength of 0.390 approximately of a metre. Now a quarter of that would be 0.097 of a metre or 97 millimetres. So that's the kind of length we would need for our tube, except remember there was that end effect. So we don't need the tube to be quite as long as that. We can take off 80% of the diameter of the tube. So if our tube is roughly 10 millimetres in diameter, we can take 8 millimetres off. So instead of having a tube 97 millimetres long, we could have one 89 millimetres long. And if we blow across that, we should get a frequency of 880 Hertz. So here is the pipe that I've ended up with, and this should be about 880 Hertz. So we want to know where that will be on the piano. So let's take a look at the piano keyboard. Here it is. Now you can see the note marked as middle C, and if you go up an octave there'll be another C, and there's a C above that. We'll get a convenient range for our panpipes by going from the C above middle C through to the C above that. So what we're going to need to be able to do is make pipes that do that C, D, E, F, G, A, B and C again. I've looked up the frequencies that we need for those notes. So here they are, and you can see there the 880 Hertz is the A on that scale, but there are all the others as well. That's a handy range for us to make, partly because the lengths of the pipe don't need us to use too much pipe, and the pipes there are fairly easy to blow, and it's convenient because it works with a very common kind of water pipe. It's a plastic water pipe that's used in central heating systems very often, and you can get it from the DIY chains like Wickes and B&Q, or anywhere that sells plumbing supplies. Here it is. It's Speed Fit plastic water pipe. When you look at it carefully, you can see that it's got a blue layer in the wall, and the cost of this at the time we're doing this recording would be £3 or £4 for 2 metres of it. It's marked as 15mm pipe. The walls are quite thick, so inside the diameter is just a little bit over 10mm. So that's the pipe that we've used, and it's fairly easy to get hold of that. Now we need to work out what lengths we want for each note, and so here they are. We've used the calculation that we did before, and we've used the frequencies for each of the notes in the octave that we want. Now you do need to try to cut the pipe so that the ends will be square, and what you might want to do is cut them very slightly long and then sand them down, and that gives you an opportunity to make sure that you can sand the ends square as you do those final adjustments. If you've got a good musical ear and a piano or a tuning device, then you might want to just sand your tubes until they sound right. Otherwise, you can sand them to the lengths that we suggest. Bear in mind that when you're blowing the pipes, the pitch will change a little bit. As you blow them, they get warm, and as they get warm, the pitch of the note will rise by a little amount. In addition to that, when you put the seal on the end, the note does tend to go very slightly flat. Now, it may well be that you don't notice that at all, but if you're sensitive to these things, you might find that you need to do a little bit of extra sanding after you've added the seal. Unless you happen to have a pipe cutter, you can cut the pipe with a hacksaw or a saw with a fine blade. And remember, you're trying to cut the pipe square, but if you cut it a little bit on the long side, then you can use sandpaper, and I put it in a block of wood, to try and sand that to make it a little bit shorter and to make it square. You'll know whether you've sanded it square because if you stand it on its end, it should stand up straight. You're going to sand off all the rough edges, and then you're going to put that seal across the bottom as we did earlier for all the pipes. And then once you've done all that, here is my set of pan pipes. You can see that what I've done is after I've made them, I've glued them onto a scrap of plywood. Any piece of wood, any flat piece of wood will do for this, and I've just shaped it a little bit so that it follows the change in length of the pieces of tube, but you don't necessarily need to do that. You do want to make sure that the tubes all stick above the piece of wood by the same amount, so the tops of the tubes are all in a straight line. And I've got the short tubes on my right and the long tubes on the left, so that they go in the same direction as a piano keyboard, for the higher notes moving to the right. So I guess we should try the notes just to see what they sound like. So working from the top. And you can use those notes to play some common tunes. Starting on the bottom note, each of these tunes will play using the pipes that you've made. So Twinkle Twinkle Little Star will work, Bar Bar Black Sheep, Amazing Grace, Kumbaya, Michael Row the Boat Ashore, and you may find others. But each of those tunes starts on the lowest note on this set of panpipes. Anyway, for now, have fun and goodbye. Who knows, with a professional instrument and a great deal of practice, perhaps this could be you.